Once again, welcome everybody. Welcome to students from Mr. Meunier's class, students from my class to our Unit 4 review. Certainly welcome to those of you that are watching this on demand. And if you're outside of Avon High School, we always welcome you to kind of tune into what we're doing, all the fantastic things that both my students and Mr. Meunier's students are doing. And we hope that this video is certainly helpful to you as well. So as you can see, the topic tonight is all about Unit 4. So from the standpoint of the course and exam description, you know that that takes us all the way from topic 4.1, which is interpreting a derivative, down to 4.7, which was L'Hopital's rule. And so it's very likely that we might hit a little bit of each of those topics. A lot of this is going to be guided by what the people that are live in my stream here are wanting. So I'm going to solicit some questions from those folks as well. But I think we'll hopefully make all of you feel a little bit better about Unit 4 once you're all finished. Then say what you might feel now. I am going to actually start. I'm going to start with a document that has a couple of problems that you don't have in your possession. So don't worry about, I don't think you necessarily need to write these down. There's just a couple of problems, as you can see, that I'm going to talk about here. I think, honestly, you can sit back and really take this in. I wanted to put something kind of forward initially so that you wouldn't have to work really hard and strain yourself to write and catch up. You're welcome to take screenshots of this if you want to after the solution is finished, if you think that that would help you. But what I'm doing here is basically outlining what we saw in our two classes, Mr. Meunier and I, the most common mistakes that were made on some of the quizzes that had been taken up until this point. And rather than just to show you the same exact problems, as we have just a few people that are still scurrying to make up some of those quizzes, I've written some questions that are somewhat like those ones that you guys had some issues with. So we're going to start with number 1 here. It comes from topic 4.2. It is a particle motion problem. And it says you've got a particle that moves along the x-axis with a position given by x of t. And we see this really light polynomial, t squared minus 4t minus 8. The position is measured in inches from the origin, and the time, which must be greater than or equal to 0, is measured in seconds. So it's not often that you have these particle motions along the x-axis that actually have units, but we're going to go with that. You're going to be asked 3 questions. First of all, find the position of the particle when the velocity of the particle is 6. Now, this wasn't a tremendous issue, but the common misconception, I'm going to always write those in red. The common misconception is that people think that this is finding x of 7. And I think it's just because you see the word position, you're thinking x, which is wonderful. You need to be thinking that. And then, oops, I'm sorry, I didn't mean to say 7, guys. How about 6? That 7 would be a misconception, but 6 would also be a misconception. And then perhaps the student sees the number 6 and immediately they think, oh, that's a time. But we have to read this, and it says that the velocity is 6. And so the very first thing that we want to do is find that time when the velocity is 6. So what is the right thing to do? Well, we're going to have to start this off by finding the velocity, which is, of course, the derivative of x. Okay, so here we've got that going. And once again, if you're just joining us, we're taking a look at a problem that you don't have in your possession here for problem 1 and 2. So don't worry about looking through your notes for it. Just kind of sit back and watch this. So the derivative of that position, hopefully by now you all are thinking, yeah, that's a pretty easy derivative, 2t minus 4. And we know that that is now velocity. We're going to set that velocity equal to 6 because that's what this says. We've translated that part of this sentence into mathematics. And we can solve the mathematics, right? We can solve this and get t equal 5. And that is the number. That is the number that we want to use. Another slightly common misconception is that a student will be way too much in a hurry and they'll plug that 5 into this velocity expression. Well, if you do that, you're probably going to get 6 because that's where it came from. But think about what we were asking for. We want the position at time 5 now. And so now you just run that 5 up there through the original polynomial expression, and you all should be good to go. 25 minus 20 is 5 minus 8. I believe that is -3, if I'm not mistaken. And that would be the position. Notice I'm not stating that you have to explain the meaning of this, but I suppose if we did, the position is measured in inches from the origin. I would suppose that -3 would likely be 3 inches to the left of the origin, but we didn't really talk a lot about the relative positioning to the origin, and I don't think you're going to have to worry about that. But that's probably what we would say here, 3 inches to the left of the origin. Okay. Now, a bigger misconception comes into play in part B, and we noticed this on the quiz. It says, find the average acceleration of the particle during the first 3 seconds. And there's really 2 different things that's going on with this particular problem. You see the word acceleration, and I know it's like you're really eager to say, hey, I know acceleration. I know that if I just start with position and I take its derivative once, I get velocity, like we did in part A. And if I take the position derivative twice, which is the velocity derivative once, that's acceleration. And that's wonderful. That's knowledge that's going to really serve you well, I think, on the exam. But when you couple the word acceleration with average, you're not in calculus class anymore. We don't want derivatives. And I know it's really difficult to kind of bounce back and forth between calculus and algebra, but we hope that you guys are starting to get more comfortable with this fact that average acceleration is the change in velocity over the change in time. Just like average velocity would be the change in position over the change in time. So at no point in this problem do you ever get to the stage where you need to take a second derivative. That's the first obstacle. And the second obstacle, sometimes this bothers students more often in certain years than others, but the phrase, the first 3 seconds. I think we had a problem on our quiz that was the first 2 seconds. And students interpreted that as from time 1 to time 2. Think about this. How many seconds have gone by from time 1 to time 2? Just 1 second. We wanted time 0 to time 2. Just like in here, we want time 0 to time 3. So remember, if you see the language, the first 3, whatever, first 2 seconds, minutes, whatever, you're going to want to start at 0. It's not probably likely the AP exam would try to be that tricky. They'll probably just say on the time interval 0 to 3. I may do the same thing on the exam, but I just want to make sure that we've taken care of that if it ever shows up in the future. So for this particular solution, we just simply take the I'm going to label what I'm doing. You don't have to do this. It's wonderful if you do, like acceleration subscript average, but that's really not necessary. But that's going to be the velocity at time 3 minus the velocity at time 0 all over 3 minus 0, right? That's your change in velocity over your change in time. And now we're going to plug in our 3 to the velocity, right? And I think I've already got that up here in part A. I'm going to highlight it so it stands out. And if I plug 3 in for this, I get 2 times 3, which is 6, minus 4, which is 2. And if I plug 0 in for that t, I get 0 minus 4. Be very careful. We're going to subtract a -4. And then, of course, 3 minus 0 is 3. And when all of this reduces, I get 6/3, which is 2. Now, I did not, I whipped this up really fast tonight, and I probably should have said, be sure to include units with your answer. We definitely want those units here. So you've got to think about whether it's average acceleration or instant acceleration with the second derivative, the units are always the same. In that case, we would say inches per second squared here, inches per second per second. Okay, so you got your two answers here so far that I'm going to box in. And that will take us to our third common misconception, which did bother a few students. I'll guarantee if this bothers you one time, you'll never miss it again. My heart will break if you got this right and then somehow later on you miss it. But hopefully that's not going to be the case. Finding the speed of the particle at time 2. Some of you are like, yeah, that's me. I messed this up. Speed has got to be sort of disassociated with velocity. I know in everyday language, sometimes we don't tend to make that distinction, but for the purpose of calculus and physics, right? Some of you are taking both. All of you are taking at least one of those courses right now. Speed is the absolute value of velocity. Remember, velocity can be negative or positive. And in our course, a negative or positive velocity just simply means that the particle moves either left or right. That's all that it means, right? We don't tend to throw things up and down in calculus like you probably would in physics. Left velocity or negative velocity is left, positive velocity is right. But when you talk about speed, we could care less what direction the particle, the ball, the bug, whatever is moving. And so we just take the absolute value of that. Now, if we're going to do this specifically at time 2, we're going to take our velocity. Let's go ahead and find the velocity at time 2, which is taking us right back to this expression here. And something very interesting happens. We get 2 times 2 minus 4, which is 0, right? Which means you would have been lucky, because if you wouldn't have known that the speed is the absolute value of velocity, the absolute value of 0 is 0. But you guys know what I'm going to do next, right? What if this question said at time 1? That's where things can really be troublesome. And just what do you think calculus teachers like to do? Do you think that we like to give you negative velocities on purpose? We wouldn't do that, would we? So in this case, right, the problem that we're actually now solving, the velocity at time 1 would be 2 times 1 minus 4, which of course is negative 2. Hopefully you all see that. But we have to understand that the speed is the absolute value of that number, the absolute value of negative 2, and that would just be positive 2. Now, one thing that speed and velocity do have in common, and that's their units. If velocity would be measured in inches per second, then speed would as well. The only difference is you make it positive. Okay. Kind of ironic that the average acceleration over the first 3 seconds is the same number as the speed at 1 second here. But that's just a coincidence with the particular function that I used. And I would like to move on to a much more recent quiz that you all may have taken over the related rates that deals with the cone. This would have been the backside of the particular quiz that we took. This is a slightly different problem, but it has a lot of the same features. It's kind of a fun problem. It's kind of making me hungry. Anybody want a snow cone? Doesn't that snow cone look good there? The melted remains of a snow cone is draining from its conical paper cup. You've all been there, right? You've all been there. You've all had that snow cone. You look down, you see all that like juice. This rate at which the sticky remnants of your snow cone is draining is at the rate of 1/4 cubic centimeter per second, right? It's coming right out the bottom here, right? You've got your blue raz, you got your cherry, and you've got your yellow. What flavor is yellow? Banana? I don't know. What is that? What is yellow? So all of that stuff mixed together, which probably at that point looks like a dark purple, is draining from the bottom. The paper cup measures 10 centimeters tall, and the top has a diameter of 4 centimeters. How fast is the level of the liquid falling at the instant the liquid in the cup is 5 centimeters deep? And as always, you will be given the formula for the volume of a cone. I applaud those students who do a good job of organizing. What I'm talking about is the students who write down, either the word given or maybe the letter G. Maybe you write the word find. Some of you just write the letter F. And then you've got equation or E. You don't even have to write the words or the letters as long as you are starting to put some of this information from the written part of the problem into mathematics. But I will tell you that if you do write the words or letters, you'll at least kind of remember which part is which. And it can be very helpful. And I did a little data analysis, and the students on this particular problem who wrote find, given, equation, or G, F, and E averaged 3.8 out of 4 points. The students who did not write any of these averaged a 2.4 out of 4. So I'm going to let you be the judge there to decide, okay, is it really important? Is there any kind of correlation between this data that he's given us and success? I would try it if I were you. All right, so given. Well, the first thing that we're given is a rate right here. And we want to make sure we understand what that rate is. We've got our equation. In fact, you guys, if I want to write this equation down, I mean, here it is. We know that that's what we're working with. Some of you have told me that in all of these problems, you would rather start with the equation because it tells you what variables you're going to use. And I like that. I respect that. The variables are got to be a V, R, or H. We have enough of them as it is. We don't want any more. So you have to look at this and think about, does this have to do with V, R, or H? And the surest way to do that is to look at its units. I've told you that you don't even have to read the problem. I don't like advertising that to students. You don't read the story problem. But by looking at that cubic centimeter, I'm hoping that the connection is made that that's got to be volume. Now, if you kind of read the melted remains of the snow cone, that would be the amount of stuff which makes up the volume of the snow cone. So this is definitely a V. And because the label is per second, then that means it's over dt. It's a rate. And so that value would be 1/4. And then you have to think, okay, is that getting smaller or bigger? Boy, do we wish it was getting bigger. Wouldn't that be awesome? Your snow cone just kept growing. But nope, not going to happen. That's got to be a negative because it is decreasing, draining. What other kinds of information do we have? Well, the paper cup measures 10 by diameter 4. And so that's something that you don't really have to put down in your given find equation. You could actually kind of start labeling your picture. Make sure you understand the difference between diameter and radius, because sometimes teachers can be a little devious. I haven't done this to you yet on a quiz. I'm not saying I plan on doing this to you, but you never know what to expect. When you've got diameter given, that's not a part of our formula. If it were me, I would change that immediately to a radius on the fly. Diameter of 4 means radius of 2. And that's going to allow you to kind of work with this problem, I think, a little bit easier, okay? It asks, how fast is the level of the liquid falling at the instant the liquid is 5 centimeters deep? That means you're finding the D. Well, what is this liquid? Well, remember I said this liquid's going to be purple, right? At some point, right? When you mix all that stuff together. And if you don't believe me, test it out, right? Go to your neighborhood snow cone store, right? Frigid Frog, I don't know, someplace. Order these flavors and you tell me if it's purple after a while. So you've got your purple liquid and it's kind of draining down to a certain level. We do not know how tall that level is as it's draining, right? We don't know this. It's an H to us. Now I know eventually it's going to be 5, but as it's draining, it's an H. So what we're going to want to find is dH dt. That is what it means for what we're finding is how fast is the level of the liquid. A lot of you in the problem that we did thought that we were finding the rate of change of volume, which was kind of strange because we had already given you the rate of change of volume, right? So know the difference between your find and given, right? Level, the word level is pretty synonymous with height, I think, all right? And we're going to find this specifically when the height is 5. When the height is 5. Okay, next stage of it. You've got your formula for your volume. We've discussed how this is a bad formula, you guys. This is horrible. The cone formula is one of the worst because of all the variables in it. If you look at this right now, it's got 3 variables. If you think about what's going to happen when we take its derivative, it's then going to have 6 variables, right? A dv dt, a dr dt, a dh dt are all going to kind of jump into the mix, and we're going to have to balance all those variables. And so we don't want that. Plus, if we want to take the derivative of this, that's going to require the product rule. Ooh, right? It's okay to say ooh. So what's going to happen? No, we're going to have to use this information about this 10 and 2. And I think on your quiz, you actually had the chance to, if I remember correctly, that was part A. You actually had the chance to find that and receive a point for it. So what we're going to do is we're going to take a look at this piece of the cone, right? I'm going to extract that image completely from the problem, labeling it as I do so 2 and 10. And then I'm going to go for the part that's just the liquid here. And I'm going to extract him from the problem. Whoa, he really wanted to fly around there on me, didn't he? And I'm going to have an arbitrary H and an R. I don't know what the H is. I don't know what the R is, because remember, this is changing, right? It's falling. Those are variables. And so now I can use any one of your proportion arrangements. You could say radius over radius equals height over height if you want. And then if you cross multiply, 2h equals 10r, or in this problem, r is going to be h over 5. Now, why did I solve for r? That's a good question. Why is r so necessary to be solved for? Well, if you look through the problem here, what's mentioned most? H. What's never mentioned? R, or dr dt for that matter. So r is the bad variable that we are going to remove and replace with this h over 5. Just like that. All right. So hopefully that's starting to make a little bit of sense there. Now, what we're going to do next is hopefully help ourselves out a bit, because you don't want to take the derivative in this form right now. It's just not ready. You're going to want to go ahead and simplify this a little bit more. I had a few students that got this far and still struggled. Go ahead and square the h over 5. I'll work this out slowly just to make sure that things are going all right. So if I work this out slowly, I'll have h squared over 25 times h. And then when this is a 3 right here, my pen's getting a little sluggish. 3 times 25, of course, is 75. And then the h squared and h is going to be h cubed. And then don't forget, I still have a pi hanging around, which I could put up in the top. I could put out here to the side. It doesn't really matter. And then I'm good to go. Now, some people didn't take a derivative on this problem. That's kind of important, right? Otherwise, you'll never get your dv dt, right? This is still all equal to v. But now when I start taking the derivative, it's pretty much home sweet home here. We're going to finish this up. The derivative of v with respect to t is dv dt, of course. The 3 comes out in front. We get 1 over 25. I got my pi. I got my h squared happening there. I got my dh dt going on. And then I can start plugging in what I know. And what I know, and that's what's beautiful about this, you guys. You don't have to go back into the problem and read the words again and run the risk of being confused. You know that the dv dt is 1/4, negative 1/4, I should say. So we'll insert that here. And we know that the h is going to be 5, which is kind of nice because that 1/25 and this 5 squared are going to cancel each other out, aren't they? As you can hopefully tell. And then that's going to leave the dH dt that I need to isolate. And so once those 25s do indeed cancel, all that's going to be left to do is divide by 4. Now be careful, make sure that when you are dividing by that 4, or I'm sorry, dividing by pi, make sure that that pi does look like it's in the bottom of this, okay? Even after explaining to students that the diagonal fraction bar is just the most evil thing that you can write on paper because it's very difficult for a teacher to discern what the meaning of that is, I still had a couple of students that did that. So make sure that the horizontal fraction bar is in play there. And since this is a rate of change of height, we just use centimeters, not cubic, not square, just centimeters for the height, and then the time, of course, is going to be seconds. You can say S or SEC. The fact that the dH/dt is negative, think about it. Unfortunately, that's going to be the case, right? Now, I don't mean to trick you, because some kids will be like, well, wait a minute. You said how fast is the level of the liquid falling? Well, if it's falling, doesn't that already imply it's negative? I'm not going to go there. I'm not going to say, oh, you should have called this positive because the word falling was already in the problem. The ACE exam is very, very diplomatic about that. They'll say, how fast is the level of the liquid changing in their questions? That way, they would expect a negative if it was decreasing. Okay, so that's probably something that I could change to make it less confusing and tricky for you, hopefully. That's all I had for the beginning part of this in terms of the common errors, but there is one more common error that already is tied to the very first problem in the Unit 4 review packet that I think you all hopefully have this in your possession that we gave in class. Eager rock fans, and for those of you who are watching this outside, I will make sure that you have a link to this document in the description below in case you want to download that and follow along while you're watching. So this particular problem is going to be calculator active, so we'll run through that aspect, but it's the interpretation part that seems to be the big misconception here. Eager rock fans enter a line to buy tickets to see the renowned rock band Sir Isaac and the Newtones at a rate modeled by the function given by E of t, which is 512.7, 512.7 e to the negative 0.17 t power. What a crazy looking function that is. E of t is measured in people per minute. T is measured in minutes, and the time interval for which this is active is 0 to 30 minutes. Maybe that's like the gates opened 30 minutes before the show. We want to find E prime of 22 and use correct units, interpret its meaning in the context of the problem. So why don't we, first of all, do the calculator work? Let's find this E prime of 22. You guys are welcome to follow along with me if you have your calculator handy. Otherwise, I've got mine here. Because this is a standalone problem, I don't think it's that big of a deal if you wanted to do what I'm doing right now, and that would be to store the function. I mean, obviously we can. I think it's a good skill to be able to do this. If you're watching this outside of Avon and you're like, what the heck kind of calculator are they using there at Avon? This is the TI Inspire. You would probably be perhaps using the TI-84, TI-83. And if you wanted to store your function, you would just do so in your Y1 equal menu. But you could also refrain from storing it and just do your normal math manipulation in your home screen. Now that we have this, on the TI Inspire, we can use the cool shortcut menu, calculus, not probability, that's a different class, calculus, and we want derivative at a point, right? Derivative at a point. Now I'm going to go back to the problem just really quickly, make sure that we are understanding this. We were given this E, we were finding E prime, so there's no question that we want to take a derivative. We want to do so at 22. So because I entered the function as t as our variable, we better stick with that. TI-84 people, you're going to probably be sticking with x. The value is 22. Once again, this is a first derivative. Hit OK. And then here, we're just going to type the function in, e of t, and we should be good to go. Right? Those of you that are using a TI-84, I think your best friend is Math 8. Math 8, I believe, is your shortcut to pull up this derivative, and then you can evaluate it at a point there. So we have negative 1.969. Notice that you can always round this up, and you could call this negative 1.97 or negative 1.970. Those would be the only three acceptable answers that have at least 3 digits that we would take. Now, granted, if you go more digits beyond the 9, we're going to ignore them, and you'd still get full credit. All right. I typically like to truncate because truncating is easy, negative 1.969. And on the AP exam, I highly encourage you to write this step out. Identify what you just found by calling it e prime of 22. You don't have to say the approximately symbols. If you put an equal, that's okay, but we would like to have that. Now, it says that you need units. If you don't put the units in the numerical answer, but they show up in the interpretation, you're going to be okay. If they show up in the answer, but not the interpretation, you could run the risk of being in trouble. So you have to be very careful there. Oh, somebody had let me know the number is slightly off because my calculator was missing a digit. 512 point. Oh, you know what? I forgot that this was 512.7. Okay, not a big deal. I am slightly off there. Let me fix that. No big deal. Add the 0.7 here. Thanks, Victor, for letting me know. New function. And then if I just take this guy and recalculate it, is that looking a little bit more like the answer key that's like right in front of me? So I apologize for that. It is negative 1.972. Negative 1.972. Let that be a lesson. Make sure you double check what you entered your calculator. You would almost think I did that on purpose, right? I didn't. So this should be negative 1.972. But as I was saying before, you want to make sure that I would put the correct units in both spots, all right? And because we already had something measured in people per minute, the derivative of that would be people per minute, or people per minute squared, okay? Now, the tricky part, the part that asks us to use correct units, interpret the meaning in the context of the problem. And what I'm going to do here, I'm going to actually see if I can type this instead, because I can do it a lot faster and not run the risk of messing up my computer and making it think too much here. So I'm going to make a font here that's somewhat readable, maybe 16 will work. So what would be the units? Well, notice how the prime mark here definitely denotes rate. And it's perfectly fine. And I think it's also a great idea to start with the words, the rate. I like the phrase at which, the rate at which. I think it sounds very grammatically pleasing. It's probably not the way that you all talk to each other, but I think it works. It's not a mandatory thing, but it's certainly going to get the job done. Now we get into our NUT. Remember, NUT is the acronym, nouns, units, time. Oh goodness, can I get back into this? Good. Nouns, units, time. And so we need to start putting in that information. So what is the noun, the subject of the sentence? Well, eager rock fans, right? Now you don't have to say that. You could just say the rate at which the fans are doing what? The rate at which the fans enter the line is, okay, now wait a minute. I'm still like one derivative here, am I right? Because remember, E of t already is a derivative. I've taken a derivative of a derivative, so I've got some more I need to say here. So if we say the rate at which the fans enter the line is decreasing by, is that going to be enough to say a second derivative? Maybe we need one more charged word here. The rate at which the fans enter the line is changing. Well, that's kind of like the same word as decreasing. Let's think about this. The rate at which people enter the line is decreasing by. If I just take that 1.972, if I put the right unit with it, people per minute, I'm into my second derivative, you guys. Because this word rate with that word decreasing, when you have the right phrase, the right words around it, is going to be fine. If I wanted to interpret E of t, and this is what really helps kids, if I just interpret E of t, tell me if I even have to use the word rate. Fans enter the line, and the problem is I don't have a number to plug in for t, but let's say I plug in something 22, and let's say I get 50. I could say fans enter the line at 50 people per minute. Never have the word rate in there, but it's a derivative, right? So that's the thing that I'm looking for here. And of course, you want to finish this up. It's so important that we finish this up with the t. So that would be at t equal, what was that, 22 minutes? That would work perfectly. Now, here is the part that it's easy to get us in trouble, all right? If you want to use the word rate twice, I'm not going to say you can't. It's just that you got to be super careful with what else you're going to say. So I'm going to type this in red to kind of indicate that this might be bad. The rate at which the rate of fans entering the line is decreasing by. That's going to have a little too much negatively derivative charged words. The rate at which the rate of fans enter the line is decreasing by. The rate of the rate decreases. That's 3 derivatives. If you want to use the rate twice, let's make sure that we modify this, and we would say the rate at which the rate of fans are in line. That kind of sounds funny. I think what we need to do is get rid of the word at which, maybe, and say the rate of fans in line is, and then you could say 1.972 people per minute. Again, it's not very grammatically correct. I'm not a big fan of it. We've been accepting that on the AP exam in the years that I've read, but I worry about whether or not the context is really conveyed well, especially the fact that the decreasing aspect isn't really coming out. So I would much prefer this. I would much prefer this be the way that you would interpret. All right, so just kind of lock this in and use the phrase, the rate at which the subject is, and then you got the word increasing or you got the word decreasing. Okay, and hopefully that'll help you a little bit. All right, we are 42 minutes in. I've got some other things that I've got planned here as far as AP Classroom is concerned, not a lot of you have gone into AP Classroom at this point and started to work on some of the multiple choice. Maybe that's kind of one of your plans as you finalize your study, which is totally okay. But for the kids that have been in, I have taken the data and found out what problems are being most commonly missed. And I have a few of those on cue to present to you here. But what I wanted to do now is just open this up to you in the chat, just send a private message. Is there any questions on the review guide? So, you know, from this number 2 with straight line motion, all the way into problems 9, 10, 11, 12 with 4, 6, and then up to 15 for L'Hopital's rule that you would be interested in taking a look at. Just send me a message in the chat and just say problem 10. Got a request for a position graph question, which I think problem 2 will probably suit the bill there. So no, it can definitely take care of that one. In fact, since that's the very next problem, I'll go ahead and start this one. And again, you guys, anything else that you've got on your mind, we can take a look at. Got a request for a problem in the linear approximation topic for 6, 9, and 10 that I'll also run through with you guys. So we're going to be in pretty good shape. You guys saved me. You asked some questions. I was kind of worried, and I was going to have to just randomly pick. All right, let's take a look at 2. Graph below shows the velocity of a particle moving along the x-axis and can be defined by a continuous linear piecewise defined function. So the thing that I want to make sure that you guys do here is highlight, emphasize, say to yourself out loud, this is a graph of velocity. This is a graph of velocity. Okay, so that's going to be really, really super, super important. We're told that v prime of t is equal to 0 on the interval 3 to 4. Now that's kind of important because otherwise you wouldn't really know that this is horizontal other than the fact that it looks. So yep, the graph is definitely equal to 0. The derivative of the graph, I should say, is equal to 0 in that interval. So what's the questions? Over which time interval does the particle move left? So the key here, translation. You take this phrase, particle move left, translate it into mathematics, v of t less than 0, right? You remember there's a page in your notes that has all of the, it has an empty box that you guys could fill in with the information. In my particular class, we didn't fill that in class, but I directed you to go to Schoology, look at the solution key that's posted there, and you could start filling in those little nooks and crannies of that. It's a great way to study. So basically, I need to know, hey, when is v prime less than 0? Well, the big misconception here is to assume that it's on these intervals. Because, hey, there's my graph. Graph less than 0 is graph underneath the x-axis. But that is the right answer. That is the right answer. Why did I take v prime here? Right? And I know some of you are like, why did he write v prime? It's because so often a kid thinks that you're always going to be given position and you have to take a derivative. We don't, you guys. The derivative is already there. So I don't know, hopefully it allowed you to kind of retrace your steps and think, no, I want where this graph is below the x-axis, right? I want just v less than 0, and I consider myself lucky I didn't have to take a derivative, at least yet, okay? So those intervals would be from 0 to 2, and just so you know, I don't want you to panic or stress about, do you include the endpoints? We're gonna read this either way. If you put a bracket here or a parenthesis at 0, we're going to be okay with either. If you want to know the big reason, kids can outsmart us, right? You can do the parentha bracket, right? Ever see a parentha bracket? That's a parentha bracket right there. Right? Is it a parenthesis or is it a bracket? So we call it a parentha bracket. So that's one of the reasons why we don't distinguish. The other reason is that certain authors define increasing differently than other authors, and that's going to be a big topic when we get into Unit 5. Notice that we're going to be below the x-axis or t-axis again on the interval 6 to 9 as well. So we're going to go ahead and state that. And then it says justify your answer. And the reason would be because, simply enough, v of t is less than 0 on those intervals. You wouldn't have to say anything else but that. And now we come to the next problem. On what time interval is the particle speeding up? Now, when you get the speeding up definition here, your mind has to think about two things. Speeding up means v and a, velocity and acceleration, have the same sign. Again, that's all in that table in your notes that you can easily call up on Schoology and fill that out, study that. So in order to make this happen, you can organize your work in a lot of different ways. And I'm not saying that this is a mandatory, but this is the way that both our classes like to teach this. We would have you do a V number line. And in this case, you can see that at 2 and 6, things start to kind of change. And we know that the velocity was negative on the interval 0 to 2, positive from 2 to 6, and negative from 6 to 9. Maybe I can go ahead and put those ending points there. Then we're going to do an acceleration number line. And if you're clever about this, guys, you'll do it right underneath from 0 to 9. And you'll start thinking about the sign of your acceleration. Now, the acceleration graph here is going to be the derivative of your velocity graph. So I'm going to kind of clean up this graph and focus on taking its derivative. And if I take the derivative of this graph anywhere along that interval, what do I know? I have a positive derivative. Acceleration is positive all the way between 0 and 3. Now 3 would be right about here, right? A little bit after the 2. And I'm going to get a positive all along there. Now from 3 to 4, something really goofy is happening. And that is the derivative is 0. So you can't have a sign if your derivative is 0, which means you can't be speeding up or slowing down because your acceleration is not changing, right? It's not affecting your velocity, I should say. Your velocity is not changing. Your acceleration is 0. So we'll just plop a 0 in there. And then we'll start looking about what's going on from 4 all the way down to t equal 8. You're going to have a negative derivative. And so from 4 to 8, we have negative. And then you can see that from 8 to 9, we're back to positive. And so now all I got to do is sort of line these up. I could actually use the magic of the Smart Notebook software, and I could put these number lines on top of each other, but I know that you can't do that. So what I'll do is I'll fill in what I feel to be those overlaps, and that would be right here, 2 to 3. From 2 to 3, we're plus up here and we're plus down there. And then from 3 to 4, acceleration 0, so that's not going to work. Here I got a negative and a positive on top of each other. That's not good, but negative, and that negative is going to be consistent between 6 to 8, it looks like. And then from 8 to 9, my signs are different again. And so we're going to say the intervals would be from 2 to 3 and from 6 to 8. Now, again, I'm not saying that you had to draw those number lines, because I'm going to tell you the number lines don't get scored. They don't earn points. They don't lose points. A number line is a tool that you can use to help organize. If you jump right to the interval, you're going to get the point. And if you justify it correctly, you're going to get the second point. And the reason is because, and I would do this to be very, very specific. Let's say V of t and A of t, let's say, are both positive. I'll let you abbreviate positive POS. and we'll use the interval 2 to 3. Okay, interval 2 to 3. I like that because what it's doing is it's not giving the student the cop out just to say V and A have the same signs, because I might want a little bit more specifics, like how do you know? Well, if you have a very well constructed number line, that's where maybe that would be good enough to give you some benefit of the doubt. But I'm going to tell you, I've graded many, many, many problems in my career where I've seen students not have a very well constructed number line. It's kind of sloppy. They can probably interpret it, but it's hard for me to interpret. So that's why this is really nice. And then if you want, you can just say V and A are both negative, right? I'll let you use the quotation marks. I'm not a fan of them. I would only use them on the AP exam if you're like really in a hurry. But you know, the bottom line is, if this is a test that you're going to take that can get you college credit, why would you want to run the risk of writing something down just to save a few seconds, because it can easily be misinterpreted. So be very careful there. So that's going to be your best answer there for part B. Okay. And then for part C, over which time interval is the particle speed decreasing? This is a great phrase, because a lot of students, when they've read this, they're like, well, Mr. Record, you never taught this. Mr. Meunier, you never said things about speed decreasing. Speed decreasing is the same thing as slowing down. It's just the antithesis of part B. And the AP exam could say either phrase: speed decreasing, speed increasing, slowing down, speeding up. So you have to really equate those as meaning the same thing. And so as you can see, you've already done the work here, you guys. You've done the work, and you can see I'm not going to write this. I'm going to just state it. But I think 0 to 2, right? 0 to 2 is certainly going to be an interval over which we had a negative and a positive there. And then can't use the 3 to 4, but I believe 4 to 6, right? I'm going to write at least the intervals: 0 to 2, 4 to 6, and I think it would be 8 to 9, right? There's many more intervals over which this particle is slowing down than speeding up. Now I'm going to make sure I check my key, because then I'm going to feel like an idiot. The key does include those. Now the key is actually, it uses inequality notation, if you've noticed it, and that's perfectly fine. You're welcome to use interval notation, but make sure justify this very similarly to the way that I justified part B to ensure that you earn full credit there. Okay, and that pretty much takes care of a graphical analysis of motion. Hopefully that answered your question. I'm going to get on to the next question here, because I don't want us to run out of time. We're at the top of the hour, so we've got 30 more minutes here or so. I don't want to go over 90 minutes because you guys don't want to watch me for 90 minutes, and it makes the video very hard to process and get posted in a timely fashion. So we had a request to go to 4.6, linear approximation. Now, keep in mind that this is, I believe, the quiz that many of you have at your possession. Maybe it's a take-home quiz that you might be doing, perhaps. So we can't really troubleshoot where your issues are until we maybe show you the key in class right before the exam. But maybe this could help you with some of the problems that you're working on. So the issue was with 9 and 10. Use a tangent line to approximate, use the tangent line approximation for f of x equal radical x at x equals 64 to approximate square root of 65 minus the square root of 63. What you don't want to do, you guys, is rely on your calculator. Please don't do that, because this is probably going to spit out some ugly decimal, and it's going to be very difficult for you to say, okay, well, where does that decimal land in here? Because it's not always going to be the one that's closest to that decimal. All right, we purposely write problems where that may not be the case. This should be a no calculator question, and it certainly would be on the exam. So what you're going to do is write that tangent line equation. So you're going to take the derivative of the square root of x which by now you've seen enough, half x to the negative half, also known as 1 over 2 root x, right? And you're going to approximate him at 64. Now, why did I choose 64? Well, think about it, right? It is the nicest perfect square that lives in this neighborhood. Now, in college, we see a lot of times that these questions will appear to students where they don't give you the x equals 64 and they say choose an appropriate x. And so that would be on you. I think in AP Calculus, high school level, we tend to give that value to you. So in this case, if that x were going to be 64, we would get 1 over 2 times the square root of 64, or 8, and then that's going to be 1/16. So boom, there's your slope, but you can't write in a tangent line until you have your point, and we only have half of that point right now, and the other half is going to be 8, which is the square root of 64. And so now we dive right into our point slope formula. Y minus our y equaling our slope, quantity x minus our x, which was 64. Okay, and if it helps, you can write the word point, you can write the word slope up there to keep track of it, but this will work fine. Remember how we like to say that the y is really going by the name L of x, because that's what we can use to approximate. L stands for linear approximation. It's using this line to approximate the curve. I'll add the 8 over, keep everything the same. If you find yourself in the habit of distributing your slope, I will tell you you're probably wasting your time, because it's a lot easier to work with this with that slope factored out. All I want here is for you to find what L of 65 and L of 63 would be and subtract them. Normally, I think in most of the homework that you've done, you've only had to find like one value and you were done. We pulled a fast one on you. You got to find 2 of these here. So L of 65 would be, well, that would be 8 plus 1/16. And then 65 minus 64, that's just 1, right? So 8 plus 1/16. Okay, well, we're going to have to get that written as an improper fraction. Maybe we will, maybe we won't. I don't know. Right now, I'll just call it 8 and 1/16, and we'll just see where that takes us, right? Because that's what 8 plus 1/16 is, 8 and 1/16. And then if we do the same thing for L of 63, I think you all can probably tell that this is just going to give you a -1 here times that 1/16. So this would be 8 minus 1/16, which, okay, if we wrote that, I guess, as a mixed fraction, that's 7 and 15/16, right? Okay, this is probably the hardest part of the problem without a calculator. And now you just subtract these 2. We could just work it like that. Oh, goodness, this takes you back to some wonderful memories, doesn't it? 1/16 minus 15/16. We can't do that, can we? Because 1 is smaller than 15. So remember how you used to do this? You would borrow from the 8, make him a 7. There's 16/16 that are floating around that you add to this 1/16, which turns it into a 17/16. I'll let you think about that for just a moment. I know that's pretty out there, but that's what it is. And now the 17/16 minus 15/16 would be 2/16. And 7 minus 7 is 0. I won't write that. And so that would be our answer, which obviously doesn't show up until you reduce it. And so you're going to get a 1/8 there. Okay. All right, and we'll take a look at this number 10 that was also requested before we move on to the next problems. It says, let G be a function given by this lovely thing, x times f of x. Tell you that f of -1 is 3, and I say that f prime of -1 is -2. Use the tangent line to G at x equals -1 to approximate -0.9. What we're doing here is we're maybe taking you out of your comfort zone a little bit and writing a function in a very general format, right? It's not this really crystal clear square root of x that you saw in problem 9. But you guys, that doesn't mean that the process is bad. And you're going to start to hear me say this a lot as the year progresses, as I don't want calculus to ever stand in the way of the calculus that you know. There's calculus in the problem. You know how to do a tangent line approximation like 9. Just do it all over again, just with a different function. So when you take the derivative of g, you have to remember that this is going to require a product rule. Why a product rule? Because this is a product, x times f of x. And so the derivative of x is 1. We can write that for emphasis, times your f, add your x, times the derivative of f. And there we go. There's our derivative. That's going to be the thing that's going to give us the slope that we need. Okay, well, where are we approximating this at? Well, it says -1 right here. So we're going to plug -1 in for x. And that's going to give us 1 times f of -1 plus -1, which I'm going to just write that as -1, right, to kind of clean that up a bit. And then I have f prime of -1. And maybe now you can start to understand why these things were given to us up here, because we're going to have to replace this f of -1 with that 3, and this f prime of -1 is going to get replaced with that -2. And so once we simplify this, 3 plus 2 is 5, and that's going to be our slope. That is our slope. Now we still have to find the y value of our function g. So basically where we are right now is exactly where we were up here where this purple dot is in the previous problem. Same process, just a little bit different function. So g of -1 is just -1 times f of -1. Well, f of -1 is 3 again, right? So -1 times 3 is -3. There's your y value. And so your point slope formula is y minus the y value equal to your slope quantity x minus the x value. And you guys have come way too far in this class. You've done a lot of complex things to lose points by forgetting double negatives. So be careful there. In fact, I would probably take a step here to clean that up. And after we clean that up, we can then start getting the y by itself, which remember we like to call L of x. And we'll swing that -3 over. And we have this. And now I think we're ready without a calculator, no calculator icon here. We should be able to approximate g of -0.9 by just simply plugging in -0.9 in for this equation. And that would be -3 plus 5. Yes, there's a little bit of arithmetic that you might have to do. Don't panic. -0.9 plus 1. 1 minus 0.9, right? That's like 1 minus 9/10. That would be 1/10, which is 0.1. And so this would be -3 plus, let's make that look like a 3. How's that? -3 plus 0.5, and that would be -2.5. -2.5. There's not a lot of arithmetic manipulation that you're going to have to do in the AP exam. There could be some pockets of it. Please don't let arithmetic be the cause of you not scoring as well as you can. If you're not great with your arithmetic skills, it's probably because you've relied on a calculator a little too soon. Push yourself. You still can. You guys can still get better at doing things like this, even at the age of 16, 17 years old. You just have to push. And lo and behold, we have an option there. So we're going to go with that one. All right. Hopefully that helps. There was a question about whether or not there are changing angles on the test. In other words, a related rate question that might deal with the rate of change of an angle. And if I were to back up into this document, I'm trying to think if there was an angle change problem here. And the closest thing I can see is this kite question, but the kite question does not feature an angle change. I'm not going to say yes or no that the test, whether or not it has one, but with your permission here, if you don't mind, Ian, I could rewrite this in like 2 seconds, and I could say, find the rate of change of the angle. All right, so I'm just going to call that find d theta dt. Find the rate of the change of the angle. And I'm going to use the same information. When the length of the string is 50. Okay. Now, I hope that even if you haven't flown a kite ever, you all know that the string is the thing that's attached to your hand and the kite. That's the whole idea, right? That's the whole idea of flying a kite, right? Holding on to it. So the string is going to be Z, and Z is 50. So if I gave you that information, still the height of the kite is 40, and the child is flying it so that it's moving horizontally at a rate of 3. So that's kind of in our given, and I know I'm kind of writing this backwards, but if the rate of change horizontally is 3, that means the dx dt is 3. And that would be all the ingredients that you really need. And that would be a positive 3 because it's moving horizontally. I mean, that's the whole point. When you're letting the string out, the kite's getting farther away. So Soka, Toa, right? Which one? Well, you definitely want to use the 40. Ooh, this is interesting now that I think about it, because they've got information about both of these. We're good. We're going to want to use this. Why? Well, if you try to use the 40 and the Z, the rate of change of Z is going to have to be known before you can pursue with the problem. I believe that is the intent of question 4, right? It's to find DZT. At what rate is the string being let out? So if you set up your equation using 40 and Z, you're going to have to answer this question first. So you have to do 2 problems in once. But if you just do the tangent, which isn't the tangent going to utilize the 40 over the x, it's going to make things a little bit easier. Tangent of theta is 40 over x. Derivative of tangent is secant squared of theta, d theta dt. And then the derivative of 40 over x, well, the 40 is just like a constant. And then you can think of the derivative of 1 over x. You've taken that many times. It's negative 1 over x squared, right? Think of that as x to the negative 1 power, right? And you get negative 1 x to the negative 2, which is going to simplify to this guy. Don't forget your dx dt's. That's a very, very pivotal part of related rates. This is a skill that we worked on during the last unit test that, quite frankly, you guys were pretty good at, right, with implicit differentiation. And so at this point, you're going to start plugging stuff in, right? You know that the x is going to be, well, you don't know what the x is, right? We know that this is 40. We know that z is 50, but hopefully you guys could see the 30, 40, 50 right triangle here, the 3, 4, 5. We're not trying to make your life miserable. We want you to be able to calculate those pretty quickly. So that x is going to be 30 squared. And of course, the dx dt is already here listed as 3. And then to find the secant squared of theta, what you would do here is, instead of thinking of this as secant squared, it's a lot easier if you think it as 1 over cosine squared, using some knowledge from your trig class, right? And then the cosine of an angle is just simply adjacent over hypotenuse. That would be 30 right now over the 50, which reduces to 3/5, but that 3/5 is going to have to be squared. He's also in a denominator, right? So that's going to be 9/25 in a denominator. but wouldn't I want to maybe kind of adjust that if I wanted to bring that over to the other side? So I could multiply, well, let me just change this. This is 9 over 25. If you put that under 1, it's 25 over 9. Maybe this is best. That's what this value is while it's on the left side, along with this d theta dt, right? It's like, why are you so far away from the equation? Come join the equation. Come join us. Come join us. Right here, that away. So now that he's like, okay, that's what I'm equal to. We would just multiply by 9/25 or divide by 25/9. So basically your answer to this, and I'm not going to simplify it. I think you guys could all probably handle this, but it's whatever you get when you take 40 times -1 over, well, 30 squared is 900 times 3, and then times the 9 over 25. Right? Because remember, you're going to multiply by its reciprocal. And there's a lot of simplification that's going to work there. I mean, my goodness, the 9 and the 900, that'll wipe each other out to be 1 over 100 pretty quickly. But there's an answer in there for you that I hope will help out there. But like I said, we're not committing. Is there an angle change problem? We're not. Just be on guard for it, right? You guys know the formulas. You guys know sine, cosine, and tangent. Just work it with this structure and you'll be fine. Okay, there was a request for 4.2 large packet skill builder question 8. Boy, you guys are making me work on that one. I have to dig that one out. I can do that. So this is an assignment that we had given at the very beginning of unit 4. We never did collect this one. It was kind of a work in progress, I suppose, for lack of a better description. But let me go ahead and throw this in here. And hopefully more of you will be like, yeah, that's probably worth talking about. So this is what we're looking at here, guys. And Zan, if I am not giving you the right question here, make sure you let me know, because I don't want to waste everybody's time. But I think this is the problem. I'm not mistaken, right? And I tell you what I'm going to do in order to save a lot of our time here. I'm going to import the key in, and I'm just going to talk about, I think I can talk about the solution here by highlighting some of the points that are brought about in the solution key. So we'll read this here together. Okay. Oh, Kinsey, thank you very much. The units for the last problem, because it's an angle change, would certainly be radians per second. Yeah. Anytime that you have an angle change, always radians per second. You don't ever have to worry about the units of being degrees. The question reads, projectile fired upward from ground level is to reach a maximum height of 1,600 feet. What is the initial velocity? And if its initial velocity were cut in half, what percentage of the 1,600 feet will it have attained? Now, I don't want to convey the idea that, you guys are going to be responsible for lots of problems like this in the test. Because remember, we tend to shy away from problems that deal with particle motion that use gravity. We're going to let your physics teachers test you on that. But I will say that there are components of this problem that is still very essential for you guys to understand the kind of motion that we will be testing you on. And so if you guys don't mind, I'm just going to kind of talk through this. The first step, maybe a difficult step, you would have to come up with the kinematic equation. This is the equation that's used to define height of an object affected by gravity using feet as the units. And so you just memorize the formula, -16 t² plus VOT plus SO initial position. Remember, those of you that have taken physics, that question or that equation is typically backwards. They start with the first part, 0 here. Now, why is it 0? Because we launched it from the ground. So there is no initial position. VO is always going to be your initial velocity. And I think that's something that we do not know in this problem. And then the -16 is just the constant that we have to remember because it's half of the gravitational constant in feet. Half of the 32 cut is going to be 16. And we put the negative always because gravity is working downward. So here's what you have to do. Maximum height. Maximum height is going to occur when something happens. All right, I don't have a ball here or an object to throw, but I do have the cap of my Carmex lip balm. How's that, guys? So if I throw this up in the air, right? Whoops, which camera am I on? This one. If I throw this up in the air, what's going to happen to it when it reaches its maximum height? It's going to stop. And so that's why the velocity is set equal to 0 here. And the position is going to have to be 1600 if that is the maximum height. And so all you have to do is you take the derivative of the position, very easy, guys, -32t plus VO, nothing difficult there. And you have to realize that he is the velocity, which means he is going to be set equal to 0. It's a problem because there's a t and a VO. That's no fun, right? When you have an equation with both a t and a VO. So you solve it for VO by adding the 32t, and you put that off to the side. What else do you know when that ball reaches the highest point? As we said, the position is equal to 1600. But remember that VO that you found earlier, that 32t, you just substituted in for the VO right there. And now you have an equation that only has a t in it. The -16t squared plus 32t squared is positive 16t squared. Divide to get 100, square root to get 10, and then the time 10 is going to be when you have that initial velocity equation to solve for. 32t, right? 32t is now 32 times 10. So you get 320. And if you're sitting there thinking, oh, it's a system of equations, that's exactly what it is. It's just a system of 2 equations that you have to solve using substitution. All right, and then part B I don't think is quite as bad because it says if the initial velocity were cut in half, what percentage of the 16 feet would it have attained? Well, now instead of 320 as your initial velocity, we use 160. We throw it back into our position equation. We take its derivative. And once again, when you reach the highest point, velocity is equal to 0, which is why we have that 0 right there. And you solve that, you get t equal 5. In other words, the object will reach its initial height at time 5 now, where before it was time 10. And you have to plug that 5 into the position equation to see how high it's going to be, which is 400 feet. Not the 1600 like we thought. And so it's 25%. Don't worry about studying this much more, you guys. You're not going to see anything like this. We don't have kinematic equations that involve gravity. But what is important about this, that you guys know that velocity is the derivative of position. A particle is stopped when the velocity is 0 or the derivative of position is 0. So all of that's going to be fairly important, I think. Okay, hopefully that makes sense. I have a problem here that is coming right off of AP Classroom that it seems to be the most commonly missed question thus far of the select few who've worked on it. And like I said, if you guys still want to do that, if you have nothing else to study, it would be in your best interest to maybe take a look at those problems. I think there is a total of 18 of them. Let me get this copied, you guys, so I can run through this really quickly. It's probably the last problem here that we do in our time. But you were given a graph that looks like this. This was problem number 4, I believe. And the question, multiple choice question, said, and The one thing bad about AP Classroom is that when I'm copying and pasting and putting into my notebook software here, it's like the graphs are gigantic and the text is like minuscule. Drives me crazy. Drives me crazy. I'm going to read this text for you because I know that you're not going to probably be able to read it very well. But it says the figure above shows the graph of the differentiable function f between 1 and 11, and I would agree with that. It also shows the secant line that goes through the point 1, f of 1. Okay, so I can see that that's the left point. And you have the point 11, f of 11. So the secant line is here, and then our curve f of x is there. For how many values of x in the closed interval 1 to 11 does the instantaneous rate of change of f equal the average rate of change? And your choices are 0, 2, 3, and 4. So what you've got to do here is just really understand what it means to be an average rate of change and what it means to be an instantaneous rate of change. The average rate of change is there for you. It's the slope of that line, right? Can we find the slope of that line? No, because we don't know what f of 11 or f of 1 is. But what we can tell is that line is, positive slope, kind of at a, I don't know if that's really a 45-degree-ish angle relative to the x-axis, but maybe somewhere between like 30-ish degrees and 40-ish degrees, just some kind of a positive slope there. And then you're going to have to like travel along the curve. Travel along this curve, if you wouldn't mind, and stop when you get to a point that the tangent line looks like it might be that same slope. And I think if you get right about here, I think we have one, you guys. I'm not saying that that's exactly where it is, but I certainly believe that we're in the ballpark, right? I believe that we could draw a tangent line there that looks like it's parallel. And then if we keep going, if we kept moving, then what's going to happen next is that we're going to get slopes that are steeper and steeper and steeper, not parallel. But then when we get to, what do you think, guys, right here? That point, possibly another tangent line would be parallel. And then we're going to be kind of a negative slope, negative slope, negative slope, and then zero slope. And then maybe, I don't know, guys, maybe another point right about there where we're going to be equal again. And so the answer to this is 3. Now, I'm just going to warn you, this problem here probably has a lot more to do with the very first lesson that we're going to do after Thanksgiving break, 5.1, the mean value theorem. But I like it in that it talks about, instantaneous rate of change versus average rate of change, which are essential ideas in Unit 4. And for those of you, there's a couple of you, I think, that are in the chat that did some problems on AP Classroom. I will say the ones that you missed are the ones that typically we're not going to test because they're sort of precursor types of problems to a future lesson in Unit 5. And so, if you are working through AP Classroom and you have trouble with numbers 4, 6, or 10, I would not worry. All right, remember there's a total of 18 questions. So 3 of the 18, that's a 6th of them, really aren't very pertinent to what we are going to be testing over. A lot of the other ones are pretty good. I think they're a little harder in some cases than what we're going to test over, but hey, why not, right? There's nothing wrong with taking a harder question. We'll do that all the time. So, but anyway, I hope this helped out a little bit. For those of you that are watching on demand, we're going to close out this stream here, and feel free to watch the video again and again if you want. But whether you're at Avon or another school, we hope that that certainly helps you guys a little bit with your preparation for Unit 4. Take care.